My name is Mike Sklash. I'm a hydrogeologist for the Dragon Corporation. We're located in Farmington Hills, Michigan. For the past decade or so, I've been doing a lot of work in nitrate-impacted groundwater, and I wanted to share that with you. Sometimes the cause is not what you think, and it's not necessarily a simple problem. Part one of this presentation is going to talk about some of the methods that I've used, and part two will be basically so. First of all, we're going to talk about legacy nitrate and the tools in part one, and in part two, going to talk about 3 case studies and summarize. So, trying to put my thoughts together. Hopefully, this all makes sense to you. So legacy nitrate was nitrate that existed in the groundwater, that exists in the groundwater, that has been there for a time, and it's not the result of current land practices. And you can see all sorts of indications of legacy nitrate in different watersheds, and you can read a lot of papers. USGS has put out a lot on legacy nitrate, like you see here, and you can see here. So if you go on the internet and you look for the U.S. Geological Survey and legacy nitrate, you'll get some background on that issue and how widespread it is. 3 main factors cause legacy nitrate. First, the amount of nitrogen used in fertilizer has increased. These are data from the U.S. Department of Agriculture. Same thing happened really around the world as the population grew. We've got nitrogen on the y-axis on the left and year on the right, and you can see between 1960 and 1980 there was an increase, a very steep increase every year in the amount of nitrogen used. And then after that, the amount of nitrogen became less. And my thought here is that people using the fertilizer were getting better at dosing it to fit what they needed, as opposed to just slapping it on in 60s, 70s, 80s. Excuse me. The second cause was irrigation. And in many places, irrigated, excuse me, irrigated land has increased and the amount of water has decreased. And we can see the irrigated acres on the left axis, the water use on the right axis, and the years on the bottom. And again, this is from the USDA. So 50s, 60s, 70s, 80s, 90s, there was more irrigated acres. In the 90s, it kind of backed off, but the water use had decreased steadily from the 70s and 80s onward. And what that meant was that we were doing better at applying irrigation water. The third reason for legacy nitrate is that groundwater travels slowly. And this is a slice through a hill slope with the hills and the stream, and we can see an aquifer, a water-bearing unit in the water table. If you're very close to the stream, that groundwater might take days to reach the stream. But if you're further away, it might take years. So what happened years ago may still be coming out in the stream. And if you go even deeper, it could be decades or beyond that. Here I'm looking at a map from a graduate student of mine, Bessie Chernokrack, in 1991, looked at oxygen 18 in the freshwater aquifer around Lake St. Clair, Michigan, and Ontario. And basically, she was able to use data from rural water supply wells and look at the isotopic content, which we'll talk about later on, to find out where the oldest water is. And if you look at this map, the numbers that are the 15s and the 16s, those waters are thousands of years old. And the waters that are the 9s and the 10s, they're about, they could be recent. So groundwater in an aquifer, if it's deep and it's got a long flow line, could be thousands of years old. So if people were using nitrate 50 years ago or 40 years ago, that water could well be in the aquifer that you are measuring the nitrate concentration in on your farm right now. It's not yours, it's a legacy. So I'm going to talk about some of the tools that we used, and a lot of them relate to atoms. Not atomic bombs, but we're going to look at the simplified atomic structure. This is what you see on the top left-hand corner. This is got 2, 4, 6, 8. So it's an oxygen atom with 8 electrons, and there would be 8 protons in the nucleus in the center. But the thing that creates isotopes, or atoms with different masses, are the neutrons. So the number of neutrons in the nucleus makes the mass of an atom change. So, for example, in this one, oxygen, you could have lighter and heavier oxygen. And the isotopes behave differently physically because of the weight. And I used to use things like apples and cars and things to demonstrate, but I thought I'd show you the Dragon golf team to demonstrate the idea of isotopes. So here we are, we're all golfers. You can see one person there has extra mass. That would be me, second from the right. And you can imagine that if we were to run, I would be the slowest. I would behave different physically. And somebody like Kevin here, who's the youngest and probably the fittest, would be the fastest. So isotopes behave differently because of the mass. And we're going to see that with oxygen, nitrogen, and hydrogen. And we use those as tools to determine whether you have legacy nitrate or not. So here's a nitrate radical, NO3. So there's three oxygens, and 1 nitrogen. And what we're going to do is look at the ratio of nitrogen with an extra neutron to the regular nitrogen. And we're going to look at the oxygen regular, which is O16, to one with 2 extra neutrons. And in the water molecule, we're going to look at same thing for the oxygen, the heavy to the light, and we're also going to look at hydrogen. So this is a normal hydrogen, so it's got 1 proton, 1 electron, and here this is deuterium. This is a heavy hydrogen. It has 1 electron, 1 proton, and 1 neutron. We're also going to look at tritium, which has got 2 neutrons, and the reason I've got it spinning is that it's a little bit different. All the other isotopes are stable, and that means that they don't change, they don't radioactively decay, but H3, tritium, does. So stable isotope concentrations are measured in specialized labs. We use concentrations in delta notation, in parts per mil. So you'll see that on the graphs. And here are all the equations. We compare the samples to the standards, and that's a lot of equations. So we're not going to think about equations. We're just going to accept that those are the concentrations. So you can see over here, there's the delta 15N, the heavy nitrogen concentration. And this is in a paper by Fogg et al. 1998, where they looked at a number of different sites that had different types of land use. So this panel here was only animal waste. So this could have been a feedlot. Fertilizer, this could have been a place where they grew crops, no animals. This is natural. This could be like in a forest. And these are septic systems. So you can see that the bulk of the N15 concentrations are up in here for animal waste. For chemical fertilizer, they're down here, and natural is here, and septic is here. So we can use these differences, especially chemical fertilizer, to animal waste, to distinguish between land use that created nitrate contamination. And more recently, people have used what's called a dual isotope comparison, where you get fields based on N15 in the nitrate and oxygen 18 in the nitrate. And this is a figure from Spalding et al. 2019. So if we were going to look at, say, a golf course where they use NO3 fertilizer or NH4 fertilizer, we'd expect groundwater, if it's impacted, to be in that nitrogen NH4 fertilizer, NO3 fertilizer area. Animal waste, say if there was some animal waste from this dairy, that would be over in here, and natural soil N would be in here. So these are the data. And what we also see that nitrate in groundwater can change naturally. It can denitrify. And if we have denitrification, we tend to see a trend of the values going like that, off at an angle of 1 to 2. So now I'm going to look at water, because the water isotopes also can give you an idea of whether you're dealing with legacy nitrate or not. So what we have here is oxygen 18 and deuterium in precipitation at Ottawa, Canada. It's got one of the longest records in North America. And I'm looking at 1974 to 1980. And here's the oxygen 18 values, the O18 values, sorry, the deuterium values. And you can see that they line up on a straight line. They're linearly related. There's a good correlation with a slope of about 8. And in the warm months, you would find these small negative numbers. In the cold months, you would find large negative numbers. So at one location, you can have a range of values over the years. Basically, when it's warm, there's not much separation when it's between the light and the heavy isotopes, but when it's cold, there is, and that's why you see this type of relationship. Globally, this is the meteoric water line here by Craig, 1961, with the slope of 8, and that includes values from around the world for meteoric water. So those are are waters that come from rainfall and snowmelt and groundwater and that sort of. And if we look at the seasonal changes, which also could be useful, you see that in the summer we have low negative values. This is for deuterium. And in the winter we have high negative values. So at each location you could see perhaps summer influence and winter influence. And also the O18 and deuterium vary based on location in terms of whether it's really cold or not. So latitude and elevation. So this is a map from the International Atomic Energy Agency with oxygen 18 values. Deuterium would have the same distribution. So I'm colorblind, just to let you know. If I name these colors wrong, you'll see, you can see them on the screen. So here, excuse me, this is runoff from glaciers in Chile. So this is going to be pretty cold. So it's down in this color here. This is beach in Bermuda, which is pretty, it's not really warm, but it's fairly warm. You're going to have kind of these values in here. And this is a little lake in on the island of Igloolik in the Canadian Arctic. And these values would be very dark blue or purple, whatever that color is, because it's cold there all the time. So that's currently, but in the past, we can also see that there are, have been changes at a location with time due to changes in the climate. This is a graph. On the left side, we've got precipitation age. This comes from a paper by Edwards and Fritz. And they look at oxygen 18 over time by looking at cellulose and carbonates, I believe, in shells. And you could see that this is what they have currently, 0 time, a little warmer here maybe, and then way down to cold 12,000 years ago. And in fact, in this area, in the lower Great Lakes, the area was covered with ice until about 10,000 years ago. And that's why the groundwater that sometimes we see at depth has this sort of value. And this is the dashed line with the boxes. It's another graduate student of mine who looked in Essex County, Ontario, and he was looking at water in the overburden with depth. So this is depth below ground, and this is what he found in the groundwater in the overburden. And you can see, you know, the same sort of change from, you know, the warmer weather to the really, really cold glacial type waters at depth. One final thing with oxygen 18 and deuterium is that in places where it evaporates a lot, you get a change in the trajectory of these relationships between oxygen 18 and deuterium. This is from Martin Mwangi's thesis in 1988. He worked in Kenya, and we've got groundwater, and we've got surface water samples that he took. And you can see that the slopes are around 5. And that's basically what you'll see if a water is evaporated before it recharges. So you'll see a change there. Then we're going to go to tritium. Tritium is a radiogenic isotope of hydrogen. again, we're looking at the Ottawa data. And the units, concentration units, are tritium units. And 1 tritium unit is 1 tritium atom in 10 to the 18th hydrogen atoms. The half-life of tritium is 12.3 years. So say if I have a pound of tritium today, in 12.3 years, I'll have half a pound of tritium. And what we did here is we looked at the Ottawa data. These are the blue dots. This is monthly, excuse me, precipitation at tritium and precipitation, and this is a log scale. So initially, when readings were first taken, it was about 10 or 20 tritium units, and then due to atmospheric testing of bombs, the value of the precipitation in Ottawa went up to thousands of tritium units. The other thing that we did on this graph is we aged the water using the half-life to July 2021. This is a project that we worked on, and it was done in July 2021. And you can see that, excuse me, any water that would have been recharged back in the mid-50s, if you applied the half-life and the time, you would now have less than 1 tritium unit. So if your groundwater has less than 1 tritium unit, it's old. The excuse me, the water from the 1963, when the test and treaty was signed, is now probably about 100 or so tritium units. And currently we're down here on the right side, where we're back to kind of normal tritium values, and you can see the age tritium is about the same. So there's not much difference because there hasn't been time to change. So we use this to try to look at the groundwater and see where the observed tritium fits in. What could it be based on the input? Another kind of principle that we use is the concept that groundwater does not mix in flow tubes. Again, we have the Hubbard section that we're showing on the left side, where groundwater flows from hills to low areas, and the different colors represent flow tubes, and they don't mix between each other. So if the water goes in here at 1 tritium concentration, it won't change except by decay until it discharges. And this is an experiment, excuse me, by Kevin Mazurek from the University of Wisconsin in a sandbox model, and he's putting dye in at various depths, which shows that you don't get mixing until you get to the discharge zone. So that's part of the concept of using tritium to determine the age. We're going to look at a few other tools. This is a more realistic toolbox. This is my toolbox. Data loggers, we find very handy for measuring groundwater levels continuously. Typically in a monitoring program in agriculture, you would monitor monthly or quarterly. You need more high resolution measurements. So this is the HPT hydraulic profiling tool that we use to get high resolution vertical hydraulic conductivity at our sites. And this allows us to get a proxy for the geology. In this case, this was sand that went down a long ways. However, it would distinguish between sandy units and clay units. And basically what happens is the probe is pushed down by the geoprobe. There's water emitted at a constant rate, and the resistance to the water being injected into the formation is related to the hydraulic conductivity. And this is what the typical output looks like for panels. We have electrical conductivity versus depth. Sand would be less conductive than clay. Clay would be somewhere over here, further to the right. The second panel shows us where the water table is, that red dot. And then we have two more places where we determine the hydraulic head. And the third panel is showing the pressure that the fluid encounters trying to get into the formation. And the fourth panel, the one on the right, shows the hydraulic conductivity in feet per day. So this would be very useful in terms of sampling to get the most, say, the fastest moving groundwater. So that's the end of part 1. And we'll be back with part 2 to talk about case studies.